Dear students, welcome to the lecture series on engineering thermodynamics. Thermodynamics is an important course for the mechanical engineers and chemical engineers. This course deals with the laws of the nature. Thermodynamics can be defined as the physical science of transfer of energy and its effect on properties of substances. In short, we can say thermodynamics deals with laws of the nature such as laws of energy conversion and laws of energy conservation. Many researchers and scientists contributed to the development of thermodynamics. The significant contributions are from Antoine Lavoisier, Sadi Carnot, James Joule, Lord Kelvin, Rudolf Clausius, and Gibbs. Antoine Lavoisier was a French chemist and is known for the identification of the role of oxygen in combustion process. He also contributed to the construction of metric systems and helped to reform the chemical nomenclature. Sadi Carnot was a mechanical engineer in the French military. He is considered as the father of thermodynamics. He published a book titled Reflections on the Motive Power of Fire. In this book, he discussed about the theory of maximum efficiency of heat engines. James Joule, this English physicist, discovered the relationship between heat and mechanical work. He is responsible for the development of first law of thermodynamics, which is nothing but the law of conservation of energy. The unit of energy, joule, is named after him. Lord Kelvin was a British mathematical physicist and engineer. He did important work in the formulation of first and second laws of thermodynamics. Joule and Lord Kelvin worked to develop an absolute thermodynamic temperature scale, and we know absolute temperatures are stated in the units of Kelvin in his honor. Rudolf Clausius, this German physicist, is considered as one of the central founders of thermodynamics. He also contributed to the second law of thermodynamics and introduced the concept of entropy. Gibbs, this American scientist, explained the laws of thermodynamics as consequences of the statistical properties of ensembles of the possible states of a physical system composed of many particles. So this thermodynamics course, the laws of the thermodynamics has wide applications. Some of the applications are, we can apply the laws of thermodynamics to thermal power plants and nuclear power plants. Not only for the power plants, we can use the laws of thermodynamics to study the behavior of IC engines and to study turbines such as steam turbines and gas turbines. And the laws of thermodynamics can be used for refrigeration system and air conditioning system, and for gas dynamics and jet propulsion, and to carry out the parametric study and the performance of the system such as compressors, nozzles, diffusers, and can be used for chemical process plants. And the laws of thermodynamics can be applied for solar thermal systems also. So these are some of the applications which we have listed with reference to the application of thermodynamic laws. And coming to the introduction to the thermodynamics, the term thermodynamics is derived from Greek. In Greek, therme means heat and dynamis refers to power or work. So this course, thermodynamics, is all about the conversion of heat energy or thermal energy into mechanical work, or conversion from work to thermal energy. So both are considered in the case of thermodynamics course. So there are two viewpoints or two approaches related to study of thermodynamics. And these approaches are called as macroscopic approach and microscopic approach. In the case of macroscopic approach, we used to consider the entire quantity of the substance together we will be considering. Whereas in the case of microscopic approach, we used to divide the substance or the matter into many molecules. We consider that the matter is made up of molecules in the case of microscopic approach. Whereas in the case of macroscopic approach, the molecular level events are not considered. So we will be considering the complete process together as a system or for the complete substance. Whereas in the case of microscopic approach, each molecule at any instant will be present at a particular position spatially, and we consider that it possesses certain amount of energy at that instant, and it is going to move with certain velocity at that particular instant. In the case of macroscopic approach, the effects of the action of the entire matter is going to be considered, right? Whereas in the case of microscopic approach, the behavior of the system is considered as the complete sum of the behavior of each molecule. So the macroscopic approach is also called as classical thermodynamics, and the microscopic approach is referred as statistical thermodynamics. Coming to the terminologies that are associated with thermodynamics course, when you study any course, we used to have a specific terminologies which refers to that particular course. Similarly, in the case of thermodynamics also, we have certain terminologies. So in the case of thermodynamics, any system or device is considered as, any device or component is considered as a system, right? And system is nothing but a quantity of matter or a region where our attention or focus is concentrated, right? Let us say this is the region where we want to study the behavior of this. So this region or the quantity of matter is what we are going to call it as a system. During the analysis of the system, we will be having either we will keep the mass as constant or we will keep the volume of the system as constant. And the things that are external to the system are referred as surroundings. So this is what we call it as surrounding. And the system and surrounding are separated by boundary, right? So boundary is the interface between system and surrounding. This boundary can be either fixed boundary or it can be moving boundary. And one more classification of boundary is also there. It can be either a real boundary or an imaginary boundary. So the boundary which separates the system and surrounding, it can be either fixed or moving, or it can be a physical boundary or an imaginary boundary. Together the system and surrounding, we call it as an universe. So universe is nothing but both system and surrounding. Together it comprises universe. Coming to the different types of boundaries, the system and surrounding are separated by an interface which we call it as a boundary, and the boundary can be either fixed or moving boundary. You consider the case now. In this case, we have a constant volume case, right? And consider a certain amount of mass is entering. A fluid of certain mass is going to enter into this control volume, and it is going to leave through this. So this is mass entry and this is mass out to this control volume. Now in this case, the volume of the system is going to be held constant, right? We are going to have constant volume. So this approach is also called as control volume approach, where there is entry of work is there, entry of heat is also there. So mass is entering, energy is entering. When mass is leaving, and along with the mass, certain amount of energy is also going to leave. So here in this study, we have considered this volume as constant, right? So here we are going to have a fixed boundary, right? This is the boundary. The boundary is not going to vary in this case. Now you consider a cylinder piston arrangement as shown in the figure. So in this case, this is the cylinder and this is the piston. Within this, we are having a certain fluid. Okay. Now the piston can move up and down. As the piston moves up and down, the boundary is not going to be constant, right? Here we are going to have a moving boundary. As the piston moves up, the volume that is going to be considered for the analysis is going to increase. Whereas the piston, if it comes down, then the volume is going to be very small volume. Okay, so in this case, we are having a moving boundary. So the boundary can be either fixed boundary or it can be a moving boundary. Now you consider an case like this. Consider a nozzle. The nozzle is nothing but in this case this is having a decreasing area of cross section, and this is nothing but a flow passage with varying area of cross section, and a fluid is going to enter and it is going to leave. Now in this case, I am going to do the analysis for this particular volume. Okay, this is a control volume, and this control volume has boundary, and there are two boundaries associated. This is the physical boundary or the real boundary. This is representing the wall of the nozzle, whereas this side, both to the left and to the right, we are not having a physical boundary. This is an imaginary boundary, right? We have considered this volume for our analysis, and within this volume we are having both real boundary as well as imaginary boundary. Okay. Now coming to the various types of thermodynamic systems. In thermodynamics, we have basically three different types of systems. One we call it as a closed system, and we have an open system and an isolated system. So there are three different types of systems are there. One is closed system, other one is open system, and the third type of system is an isolated system. Let us discuss about these systems in detail now. Coming to the closed system, in the case of closed system, we say like there will not be any mass transfer between the system and surrounding, whereas there will be an exchange of energy between the system and surrounding. Now you consider this diagram. Here we have represented there is energy that is entering, heat that is entering in. Q refers to heat, and this is in the subscript we have written as in, means Q is entering in, and here heat is leaving out. So there is energy entry and energy leaving, and there is an work output from the system also. So there is energy transfer in the form of heat as well as in the form of work. And now you consider there is no mass transfer, there is no entry of mass, and there is no exit of the mass from the system to the surrounding. So such systems we call it as closed system. Some of the examples for the closed systems are, now let us say if you are going to consider a fluid present inside a cylinder piston arrangement, right? So this is the cylinder and this is the piston inside which we are having a fluid. This can be a hydraulic fluid or it can be a pneumatic fluid. So depending upon our application, we will be using either an oil or a gas. So now the system, the substance that is going to present inside the cylinder and piston, so that is not going to be exchanged with the surrounding. So it is going to be contained within this region, right? So the piston is going to move either out or it can come in. So during the to and fro motion, the volume of the system is going to may increase or it may decrease depending upon the movement of the piston. But there is no exchange of the mass between the system and surrounding. Here the system is nothing but the cylinder piston arrangement, right? So it is not going to leave the cylinder. Okay, this is an example for a closed system. Now you consider a hot water in a container. Okay, assume that this water is maintained at a temperature of 60 degrees C. So surrounding temperatures, let us say surrounding is at a temperature of 30 degrees C. This is at a temperature of 60 degrees C. And this container is closed, right? So there is no exchange of mass from the system to the surrounding. This complete container is going to be the system. Now inside which we are having this substance, and we are not pouring water. So if that is the case, there is no exchange of mass from the system to the surrounding, and we are also not going to pour anything from the surrounding to the system. So there is no mass transfer. But this is at a temperature of 60 degrees C, whereas the surrounding is at a temperature of 30 degrees C. If there is a difference in temperature, definitely there will be heat transfer is going to occur. When heat transfer is going to be there will be loss of energy from the system to the surrounding. So after a certain time period, what will happen? The temperature will decrease from 60 degrees C. So that means what? Here from the system to the surrounding, there is energy transfer that is occurring because of the fall in temperature as the heat transfer occurs, but there is no transfer of mass. So this is an example for a closed system. So in the case of closed system, we will not be having any mass transfer, but we will have only energy transfer. The another example for the closed system is you consider a complete refrigeration system inside which a refrigerant is flowing, right? And this refrigerant is not going to come out. Only during the case of leakage, the refrigerant will come out to the surrounding. Assume that there is no leakage in these pipelines or in the flow passage. So the refrigerant is going to flow through various components of the refrigeration system, and it is going to undergo different processes. But the mass that is contained within this flow passage is going to remain same. So if you are going to consider this complete refrigeration system as a thermodynamic system, then the mass that is present inside this is fixed. So it is not going to vary because there is no exchange of mass from the surrounding to the system or from the system to the surrounding. So such systems we call it as a closed system. Now let us discuss about an open system. The second type of system is an open system. In the case of open system, we will be having a fixed volume, and there will be exchange of mass and energy, both takes place. Now you consider here, so there is entry of heat and exit of heat from the surrounding to the system as well as from the system to the surrounding, and there is also exit of work from the system. So work output is also there, and there is entry of mass and there is exit of mass. So both mass transfer and energy transfer occurs in this case. So such systems we call it as an open system. Some of the example for the open system are, let us say if you are going to consider only the compressor component, or if you are going to consider only the turbine part, a boiler, a pump. In all these cases, we will be having entry of mass and entry of energy, and there will be exit of mass and exit of energy. So this is an example for a compressor. In the case of compressor, assume that this is an air compressor. This is entry of air and this is the exit of air. As the air passes through the compressor, because of the interaction with the rotor of the compressor, there will be energy transfer from the rotor to the air. So compared to the exit air, compared to the inlet air, exit air is going to possess higher energy. And there is entry of air and there is exit of air. So now the volume is what we are going to consider as a system, and this system is an open system. So there is entry of mass and there is exit of mass, and there is entry of energy and entry of, and as the air leaves, it is also going to carry away the energy. In the case of turbine also, turbine is normally used for producing mechanical work output using some fluid. Now assume that products of combustion from the combustion chamber or a steam as the working medium is used to drive a turbine. So let us say when the steam is going to enter into the turbine, it is going to enter with some amount of energy, and after driving the turbine, it is going to leave with an energy less than the entry. Right? When it is enter, it is going to enter at a higher energy, and after driving the turbine, the fluid is going to leave with less energy. So there is energy in and energy out, mass in and mass out. So this system is an open system. You consider the case of a boiler. In the boiler, the purpose of boiler is to produce steam. To produce steam, we have to supply water, and the water has to be heated with the help of combustion inside the boiler. For combustion, we require air and fuel. So air and fuel is supplied for combustion. Because of combustion, there will be generation of heat. Because this combustion process is an exothermic reaction. From the exothermic reaction, heat is going to be produced. That heat is going to convert the water into steam. So water will become steam, air will become flue gas as the products of combustion when it leaves the boiler, which we call it as a flue gas. And when the fuel, let us say we are going to supply coal as the fuel, after combustion, we will be having deposit of the ash. So we will be removing the ash from the combustion chamber of the boiler. So there is mass entry and energy entry because of the combustion, and there is the exit of mass in the form of steam, flue gas and ash. When the steam leaves or the flue gas leaves, it is going to leave with certain amount of energy. So energy is entering in, energy is leaving from this control volume, mass is entering and mass is leaving. So these are some of the examples for open system. Okay, now let us consider a pump. This is an example for a pump. We have represented using this schematic diagram. This is the suction side of the pump and this is the discharge side of the pump. So a liquid is entering in and it is going to leave out. To drive the pump, we have to supply work as the input. So this is the shaft work which is supplied as input to drive the pump. When we drive the pump, the liquid that is entering in is going to enter with some less amount of energy, whereas it is going to leave us higher energy. Here the energy is nothing but pressure energy. The purpose of pump is to increase the pressure of the liquid that is entering, and it is going to leave out at higher pressure. Okay, so pressure energy is transferred, or finally the liquid is going to leave at higher pressure. It gains energy and leaves at higher pressure. So there is entry of mass, entry of energy in the form of shaft work, and there is exit of mass along with energy. Right? So energy is also leaving, mass is also leaving. So this is also an example for open system. In all the cases of open system, we are going to maintain fixed volume. In the case of open system, we are going to have fixed volume. So the concept of control volume is applied for all open systems. When I say control volume, it is nothing but the volume of the system which is under study. It is going to remain constant, and we are also going to have a control surface. The surface that bounds the control volume is what we call it as a control surface. So this volume is held constant in the case of study. Now you consider a water heater. Cold water enters into the water heater, and inside this assume that we are going to have some electrical resistance coil which is going to generate heat. Thereby the water gains heat and it is going to leave as hot water. So when it is going to leave, mass is going to leave and energy is also going to leave. And for this open system, so this open system, this is the control volume, and this surface we call it as the control surface. So mass is entering, and from the heater, heat is entering so into the control volume, and after gaining the heat, the water is going to leave. When it leaves, it is going to carry away the thermal energy also. At a higher temperature, it is going to leave. So mass is leaving and energy is also leaving. Coming to the last type of system, this we call it as an isolated system. In this case, we will have a fixed mass. There is no mass transfer between the system and surrounding, and we are also not going to have energy transfer between the system and surrounding. That means if you consider this as a system, an isolated system, there is no mass exchange or there is no transfer of mass between the system and surrounding, and there is no energy transfer between the system and surrounding. That means what? If you are going to consider our entire universe as a system, then we can say this type of system as an isolated system, because there is no exchange of mass outside the universe into the universe, and there is no exchange of energy from outside the universe into the universe, because entire universe we are going to consider as a single system. So if you come to the practical applications, most of our engineering devices are going to be considered as an open system, where we are going to have both mass transfer and energy transfer between the system and surrounding. Now let us recap. Let us have a quick recap. So the thermodynamic systems basically depending upon whether the mass is going to be kept constant or volume is going to be kept constant, it is classified as systems with controlled mass and system with controlled volume. Under systems with controlled mass, it can be a closed system or it can be an isolated system. In the case of closed system, there is no transfer of mass, only exchange of energy is going to be here. In the case of isolated system, there is neither energy transfer nor mass transfer. Whereas in the case of an open system, right, open system where only the volume is going to be controlled. So in the case of open system, we are going to have both mass transfer and energy transfer between the system and surrounding. So most of our engineering applications, we used to have predominantly open system. So now let us have a different view by which we classify the different types of systems. Now consider that there is a system which has energy transfer between the system and surrounding, and there is no mass transfer between the system and surrounding. Such system we call it as a closed system. And the other combination is that assume that there is energy transfer between the system and surrounding, and there is also mass transfer between system and surrounding. Such systems we call it as an open system. And let us say if there is no energy transfer and there is no mass transfer between system and surrounding, then such systems we call it as an isolated system. So there is one more combination that is available where we may not have energy transfer and we can have only mass transfer. But in reality, practically we don't have such system. So there is no system where only mass transfer occurs and there is no energy transfer. That means the bottom line is that when there is an exchange between system and surrounding, definitely there will be energy transfer. In reality, we are going to have only open system and closed system, and in both the cases, if you see, there will be energy transfer between system and surrounding. But the chances of mass transfer, you can have either mass transfer or you may not have mass transfer, right? So mass transfer is either it is possible or you cannot have mass transfer, but definitely there will be energy transfer between system and surrounding. So the interaction between the system and surrounding, it can be either by means of mass transfer and energy transfer. And among these two, energy transfer will be there definitely, but mass transfer may be there or may not be there. If mass transfer is there along with energy transfer, then we call that system as an open system. If there is no mass transfer and only energy transfer is going to be there, then we refer that system as a closed system. Okay. So coming to so till now we have discussed about different types of systems, right? Now let us see this systems, it has to undergo a process or a cycle. Only then we can achieve a certain amount of work can be done, or our useful applications of our engineering devices come into existence only if this undergoes a process, the system undergoes a process, or if it undergoes a cycle. So before that we should know in what state the system is present. Okay, so see, you should know the state of the system, the initial condition of the system, and when it undergoes a process, then it will go to another state. So there will be continuous change of state, right? The condition of a system is what we call it as a state of the system. So a system is said to be either exist in a particular state when the properties of system have a particular value, right? When it has a definite value of property, then we say that the system is going to exist in a definite state. So to define the state of the system or to define the physical condition of a system, we need to have properties. So properties are nothing but the coordinates which describes the state of the system. So now you consider a cylinder piston arrangement. Inside this we are having a fluid. This is the cylinder and this is the piston. Within this we are having a fluid, and assume that the mass of the fluid is 1 kg and which is held at a temperature of 80 degrees C, and the volume of the system is 0.25 meter cube, right? So now I am defining the state of the system. To define the state of the system, I am telling that this state of the system, it is hot because its temperature is 80 degrees C and its volume is 0.25 meter cube, right? So these are referring to the state of the system. To refer to the state of the system, we need to have property. So the properties are again divided into two categories. One we call it as an intensive property, other one we call it as an extensive properties. In the case of intensive property, these properties does not depend upon the mass. The properties which does not depend upon the mass are referred as intensive properties. Some of the examples for intensive properties are pressure, temperature, density, etc. Now you see, now you consider the position of the piston is at this location. Now if you are going to connect a pressure gauge to this system, then it is going to indicate certain amount of pressure. Now let us say it is indicating a pressure of 1.5 bar. Okay, so this is referring for the complete mass of 1 kg and for a volume of 0.25 meter cube. Now you assume that I am going to introduce a very thin, right, very thin boundary, right, which is going to separate. A very thin sheet is going to be introduced here and it is going to separate these two. So now what will happen to the mass? Mass is going to reduced. If you are going to consider only this as a system and this as a system, mass is going to be reduced. Under such case also, if you measure the pressure, it is going to indicate 1.5 bar. So that means the pressure is not going to depend upon the mass of the system, right? So if you measure pressure with a separator or a wall here, it is going to indicate the same pressure. If you remove the wall also, it is going to indicate the same pressure. So it does not depend upon the mass. The property pressure does not depend upon the mass. Now you consider the case of property temperature. I have told you that this is maintained at a temperature of 80 degrees C. If you measure the temperature from this place, it is going to indicate 80 degrees C. Now I am going to take a part of water from this, right? Assume that instead of 1 kg, I have removed 200 grams from this. That 200 grams, if I measure the temperature, that is also going to indicate 80 degrees C, where the mass is different. It is 200 gram only. When it was 1 kg also, it was indicating 80 degrees C. When it has become 200 gram, it is also indicating 80 degrees C. That means the property temperature does not depend upon the mass of the system. Similarly, if you measure the density of this, right, I am going to take a small sample of the fluid that is present inside this, right, and I am going to measure the density. So whatever the density for the entire mass, that is going to be the density for the small quantity of sample that we have taken out. So there are certain properties which does not depend upon the mass of the system. Some of the examples for the intensive properties, these properties does not depend upon the mass of the system. Okay, so the example for the intensive properties are pressure, temperature, density, etc. And there are certain properties which definitely depends upon the mass of the system. Now you take the case of volume, right? Now I am telling for 1 kg of mass, volume is 0.25 meter cube. Now I am going to, let us say I am going to take out the liquid that is present here. I am going to take out 500 grams from this. Then the 500 grams will occupy half of the volume of this, right? That means depending upon the mass, the property volume is going to vary. Higher the quantity of matter, then it is going to occupy more amount of volume, right? So depending upon the mass, the property volume is going to vary. So such properties we call it as extensive properties. Properties which depends upon the mass are called as extensive properties. There are also other properties like enthalpy, entropy, internal energy. These are all considered as extensive properties because in all these cases we are going to have these properties depends upon the mass of the system. Now you have two different types of property. One is intensive property, other one is called as an extensive property. If the extensive properties are going to be divided by mass, or when I say the extensive property per unit mass, then that will become an intensive property. For example, we have volume, right? Volume is 0.25 meter cube. And now let us say I am having a volume of 0.5 meter cube and the mass is 2 kg. So this volume by mass, that is nothing but specific volume. So whatever may be the quantity of mass, finally if you convert into per unit mass, then that property will become an intensive property. Right? In the case of specific volume, I have told you that assume that you have mass 1 kg, mass 2 kg, mass 3 kg. There are 3 cases. And the volume is going to be 0.25, 0.5, 0.75 meter cube. Now in all these cases, if you divide by mass, you will get the same value. Right? If you are going to divide the volume by means of mass, then you will get the same value, 0.25 by 1, 0.5 by 2, 0.75 by 3. Everything will give you the same value. So in the case of unit mass, your extensive property will become an intensive property. This is applicable for other extensive properties. Like let us say if you are going to have enthalpy, if you divide by mass, then we call it as a specific enthalpy. If you are going to have a property entropy, entropy is an extensive property. If that entropy is going to be divided by mass or for unit mass, this will become specific entropy. When it becomes specific entropy, then it will become an intensive property. So we have studied about what is a state, what is a property. Now this system, when it is at an initial state and when it undergoes a process, it has to undergo a change of state from its initial state to final state. Right? So when the system performs an operation or when it undergoes a process, then the properties of a system will undergo a change. Right? That change is what we call it as change of state. Okay. So now if you can define the change of state, the succession of the intermediate states passed by the system during a change of state is what we call it as a path. Right? So we started with a system, then we discussed about the condition of the system, which is nothing but the state of the system, and to define the state of the system we require a property, and now the system is going to undergo a change of state. Right? When it undergoes a change of state, then the loci of the intermediate states passed during the change of state is what we call it as a path. So if you are able to define the path, right, if you are able to describe the path, then we call it as a process. Now let us say we say that normally a system is going to undergo an isothermal process. That means during that process the temperature is going to remain constant. The process can be isobaric process. If the process is isobaric process, then the pressure is going to remain constant. So depending upon the property, some of the property may remain constant and some of the property will undergo variation. Right? So we can have either one property or more than one property undergoing variations when the system undergoes a process. So process is nothing but change of state, and when the system undergoes a change of state, it is going to follow a path. If you are able to define the path properly, then we call it as a process. So we started with system, then we discussed about the state of the system, then change of state, then path, and then we have come to the process. And finally we have a cycle. Right? Cycle is nothing but many processes in such a way that the initial and final states of system are going to be the same. Right? That means a system is existing which is at the initial state. Now it is going to undergo a change of state, which we call it as a process. If you define the path followed by a system, then we call it as a process. Similarly, it is going to undergo many processes, and finally it is going to come back to its initial state. Then the sum of process or the series of processes together we call it as a cycle. Now let us explain this using a PV diagram, right? A pressure volume diagram for a system which is going to undergo many processes. Right? So now I am going to represent the variation of pressure and volume for a system when it undergoes a process. Right? So now let us consider a system which is at initial state, state 1. Now for this system, its corresponding pressure at state 1 is P1, its corresponding volume at state 1 is V1. So this is the initial state of the system. Now this system is going to undergo a change of state. From state 1 it is going to come to state 2. Right? So this is the initial state, and when it undergoes a process it reaches state 2. Right? At state 2 the properties of a system are pressure is P2 and volume is V2. At state 2 pressure is P2 and volume is V2. Now from initial state 1 the system has come to state 2 along path A. Let us say this is path A. Okay, the system has undergone a process or it has undergone a change of state along path A from state 1 to 2. Now this is going to undergo from state 2, it is going to undergo another process. Second process the system is going to undergo. From state 2 it is going to undergo the second process. Assume that this is going to, during the second process it is going to follow the path B. This is path B, and the system is going to come back to its original state, state 1, from state 2 during the second process. Right. So this is state 1 and this is state 2. The process initially is at state 1. The system is initially at state 1 and it undergoes a process along path A and it reaches state 2. And it undergoes a second process along path B and it reaches state 1 again from state 2. So these dotted lines represents the successive intermediate states. Right? The properties of the system can be identified in this PV diagram at the successive intermediate states. So now there are two processes involved. One is process from 1 to 2 along path A, and the second process is process 2 to 1 along path B. So now there are more than one process involved, and the initial and final states of the system after undergoing the process is the same. So this we call it as a cycle. So cycle is nothing but more than one process will be there. In this case we have considered only two processes. It is not necessarily only two processes. You can have two processes or three processes or four processes. We can have any number of processes. But if the condition is that if the initial state and final state of the system are going to be the same, then we say that the system has undergone a cycle. So in this case there are two processes, and if you are going to consider these two processes together, then we call it as a cycle. So we started with what is a system, then what is the state of the system, what is change of state, what is a process, then what is a cycle. Okay, these are some of the terminologies related to thermodynamics. So thank you for joining this session. Let us continue in the second lecture.